All right, everyone, this is our second lecture about the dynamic shoreline. And I'll just remind everyone that you want to have watched Dynamic Shoreline 1 before watching this one, and you'll want to have also answered the questions that are accompanying on D2L, all right? Make sure you're keeping up with those questions because those questions are going to be part of your quiz grade. So in our last lecture, we talked about the idea that we have this dynamic shoreline, dynamic meaning changing. Our shoreline changes quite a bit. And we talked about some of the forces that, that cause these changes. One of the really important forces that we have is the longshore current or the longshore drift. This idea that as waves come in, they don't come in straight, they come in at an angle because of diffraction, things like that, and that we end up with a current that basically starts to move along the shore, and it can move people if they're swimming. It also can move sand, so we end up with sort of a river of sand that goes in the direction of the longshore current. And when that happens, sand is carried from one place to another, and it can form all sorts of things like this spit, right? So we also talked about the idea that that people try to change how longshore currents affect their property, and how sometimes that is very disruptive to other people's property. So remember, this was Sea Island here, and this was the groin that was built in the early 90s. And basically this is capturing sand here, but it is starving this part of the beach from sand because this part of the beach is fed by the longshore current of this part of the beach, and normally that sand would get just carried down along this and feed this, but this groin prevents the sand from getting around it, and this sand can't get here. So you can see how much this has changed. We talked a little bit about rip currents and how they are fed by waves on either side, currents on either side, and this is basically where the force of those waves is escaping. We talked about the anatomy of a beach and how we have offshore of the beach. We have the near shore, which is where the breakers are occurring. And then we have the shore, which is sort of like this swash zone. We have the part where the swash it regularly occurs. And then we have this back shore that really only gets wet on very, very high tides, such as spring tides or during storms. Quite often, the beach is backed by dunes, and that dune can be cut into a cliff when we have very, very strong waves as well. Another thing to remember is that we often have these longshore bars here. And these bars, they're called longshore because they occur along the shore. They're parallel to the shore, and so they're separated from the beach by a trough. This is very, very common. It's a pattern we see over and over on beaches around the world. We also talked about the idea that we have beach profiles that are predictable over the course of a season. How we have summer beaches that have dunes with a berm and then sort of a steep slope down into the water. And then we have winter beaches where that berm is carried away by stronger waves. So the sand that was here gets carried out here to this bar. So you often have a larger bar during the winter here, all right? And this causes the water to often reach right up to the dunes. So it's almost like at high tide that beach has disappeared in winter. And we saw a great example of this from Superstorm Sandy, where the blue would be our summer beach with a berm here, right? And then after the storm, which would be equivalent to a winter storm, all of this, everything right in here, this was all sand, and it's all gone. It has been carried, out towards the ocean. It's been carried offshore. So these patterns are predictable over time, over seasons, all over the world when we talk about sandy beaches. Today we're going to start by talking about dunes. So dunes are found behind the beach. So if this is a barrier island here, we have the ocean and our beach, little berm here, right? And then we have a series of dunes. And these dunes have a predictable pattern, all right? So they're formed by winds that blow sand from the beach, from the dry parts of the beach. Wet sand doesn't move very much with wind, but dry sand will get blown from the beach up onto the dunes. They typically have this, what we call a sinusoidal pattern, which is sort of like an S curve, all right? So we have these S curves here where you tend to have dunes, and then these are called swales. These little valleys are called swales. So you have dunes and swales and dunes and swales, okay? We have a series of dunes that occur starting at the beach here, all right? We have little baby dunes here that are called foredunes. These would occur if you have like a rack line, stuff that's washed up, seaweed, things like that have washed up to the top of the beach. They act as a windbreak and sand starts to collect behind them. And these are just little baby dunes, so we call this the foredune. And then we have our first big dune. This is the primary dune, and we tend to see vegetation that occurs on these. That little baby dune, these foredunes don't tend to have vegetation on them. But then these big ones have vegetation on them, okay? Then we often have a secondary dune ridge here, or even a tertiary, even more beyond that, okay? And then we have these swales in here, all right? This can often, after the dunes, we often find back dunes. We find maybe uplands here, okay? And then if this is a barrier island, quite often we'll find this is the back part of the island, and we'll see a salt marsh back here. And this is really typical of what we see here in Georgia. This is exactly what our barrier islands look like here in Georgia. So let's think a little bit about what we see happening in dunes. First of all, we see a lot of vegetation on dunes. Dunes owe a lot of their existence to the vegetation that's on them because vegetation traps wind-blown sand on the downwind side and promotes dune growth and stability. If we didn't have these plants here, these dunes would be much more subject to being blown away by the wind. So these plants stabilize the dunes. Where we have places where we don't have vegetation, we often have things that are called blowouts. So this is along the coast of, I believe, California. And you can see we have lots of vegetation here. And then we have a blowout, okay? And this blowout occurs when we don't have vegetation holding the sand in place. So we often see these blowout areas. Now, dunes develop well under certain conditions. Sand needs to be abundant. You need to have onshore winds. So that means winds coming from the ocean towards land onto shore. And they need to be relatively strong and persistent. If they're not strong enough, they're not going to carry sand from the beach up into the dunes. Dunes tend to form best where we have a large tidal range, and also where the beach is wide and gently sloping, because that gives a lot of sand for the wind to grab and carry up into the dune. And in our picture here, we have, this is called a sand fence, and quite often people will put these up where vegetation is not quite so strong, and they're putting this up to try to capture some of the sand that's being blown. This is the beach here, so the wind is blowing in this direction. They're trying to capture some of this sand right behind this right behind this fence by causing a windbreak, okay? So this is a sand fence here in the dunes. So dunes move, they migrate. If we have, for example, up here, if we have the beach here, dunes will migrate from the beach away from the beach. All right, so here in Georgia, for example, if this was east, they are migrating slowly from the east to the west. And what's happening here is that wind is blowing in this direction. The sand is basically being bounced up this slope, okay? And as the wind blows persistently, a particular grain of sand moves up the slope. And this process is, I love this word, it's called saltation, okay? So it's when sand is basically bouncing up the windward side of a dune. And it will collect up here at the top. But eventually this will get too steep. And when that happens, and by too steep, I mean 34 degrees is what we call, it's called an angle of repose. If it gets steeper than 34 degrees, what happens is this sand slides down. Okay, so it collects up here and eventually it slides down. And that, when it slides, it is growing the dune in this direction. Okay, so we see a pattern of dunes that start here and sand is being basically pushed up it, pushed up it, pushed up it, and deposited here. And so our dune grows in this direction, okay? Now, we can see this if we model this in a wave tank. So now this is in the water, but just imagine this water is wind, okay? It's a lot easier to do this in water, so they're modeling this in water. And we have here, this is a dune, okay? And the water is flowing from your left to the right. So that's sort of like the wind blowing from the left to the right, okay? So let's see the process of a dune migrating. You can see this really is the shape of a dune, where we have sort of a steep drop off here, and we have sand that is bouncing up the slope of it until it gets too steep here and then slumps down. This is very, very classic. This is what dunes look like as they migrate. So what's it like in the dunes? Well, dunes are actually very, very harsh environments. Sand moves a lot. So if you've ever walked in sand and it's sort of unstable, it's an unstable environment for things that are trying to grow there. It's very, very salty because we have a lot of ocean water. We have ocean spray that's being carried inland into the dunes. So remember we talked about the idea of osmosis and how if you have an environment with a lot of salt, that water will move towards it. So that means it's very hard for a lot of organisms to live in this environment because they get desiccated. Think about if you've been to the beach and you get out and you're just like, your skin is dry. That's because the salt is drawing moisture from you, okay? So that's true for organisms that are trying to live there. It's not very pleasant for them. It is very hot in the dunes. So especially here in these swales. So this sand, if sunlight is coming down from above, we have solar radiation coming down, this sand will reflect it back up. And so if you're an organism in here, you have solar radiation coming from above and coming from below. So solar radiation is very, very strong. And especially in these swales, these can sort of get concentrated solar radiation. So it can get really, really hot in here. So it can be 20 degrees hotter in the swales here than it is over on the beach or up here on the top of the dunes. So super, super hot. It's also very, very dry because, well, this sand doesn't have very much organic material in it. And organic material is one of the things that captures moisture after it rains. So if it rains in these dunes, it's just sand, and water will actually, when it penetrates here, it just will filter straight down and it won't stay up here where these plants are growing. So these plants are dealing with some very, very dry, hot, salty conditions and in an environment where the very ground below them is shifting. How do plants deal with that then? Well, plants that live in the dunes are adapted to life in this very, very difficult environment. And one of the ways that they deal with this is they put out what are called runners. Okay, and certainly there's more technical words for this, but for our purposes, we're just going to call these runners. So this is an example of this. This is a dune plant, and you can see that these are all occurring sort of in a straight line because these have an underground root that connects all of them. So we have a mother plant here, looks like it's the first one that grew, and it shot out a root in this direction, and that root is growing underground. And every once in a while along this underground root, it's shooting up one of these. These are called ramets, okay? And so these are almost like little daughter plants. And so this allows plants to move along with the sand. Imagine that this mama plant here, the sand piled up on it and covered it up, right? So that's okay because this part of the plant can die because the rest of the plant is moving away from that piled up sand. All right, so this allows this plant to take advantage of being able to move along with the sand. And also when we have these runners or these rhizomes here, they can carry water and nutrients from one part of the plant, like over here, maybe it's moisture. So they can carry water from over here all the way over here. Okay, so this allows it to deal with some of the difficult conditions here in the dunes. Having runners like this is a really classic technique for dune plants. Lots of them have these. You see this very, very commonly in the dunes. Another strategy that dune plants have is doing their best to prevent water loss because it's very, very dry here. They'll do all sorts of things to keep what water they can collect inside of their bodies. So we see succulents here. If you've heard of the idea of having a succulent plant, succulents are plants that basically are really good at storing water and good at not losing it. Some of the strategies would be having a waxy coating. So we actually have a lot of this, even around the College of Coastal Georgia. This is called pennywort. It is a plant we see very often in the sand dunes. And see how shiny it is? That's because it has sort of a waxy coating. So the water that's in it doesn't evaporate up out of it, even when it gets really, really hot. That wax is holding the water in. We also see reduced surface area. So with things like, see this little guy right here, he has really small leaves. Leaves are great for photosynthesizing, but their large surface area, a lot of transpiration occurs there. In other words, they lose a lot of their water through their leaves. So this plant is reducing the amount of photosynthesis that it can do, but it gains being able to hang on to water. So it's basically sort of like getting rid of one benefit to have another. It doesn't photosynthesize very efficiently, but it holds on to its water. These plants are also really good at water storage. For example, this guy has really beefy stems where he's storing water, all right? And a lot of times the roots are very, very beefy as well to hold on to water. One of the things you'll notice about both of these plants as well is that they have runners. So this guy, like this leaf and this leaf, they're connected by an underground rhizome or runner, okay? If you have these in your garden, pull them up. You'll be able to see those rhizomes. This is also doing the same thing. A few other examples of strategies for dune plants. A lot of dune plants are not bright green. They're actually gray. And they will use this strategy that costs them a little bit. They don't photosynthesize as well as deep green plants. But this gray color allows them to reflect sunlight so they don't get too hot and they don't absorb too much of that solar radiation and dry out. We see them being what we call prostrate. So they are low lying. Okay, so they don't stand up. They don't stand up proud. They lay down. That keeps them from losing too much moisture to the wind. And then we also see that quite often dune plants will have really, really long roots. So these are the little plants here, and these are their roots. So you can see their roots are like, I don't know, 10 times as long as the part of the plant that is above ground. And this allows this root to be stable because you have a lot of sand that's moving, but also allows it to collect water from its surroundings. So it's very, very good at collecting whatever water is there. Let's transition from beaches and dunes to barrier islands. Barrier islands are really important to us here in Georgia because our entire coast is composed of barrier islands. So this is the coast, the border here with South Carolina and the border here with Florida. And what we see in Georgia, this is about 100 miles here, and we see that the coast is just dotted with a series of relatively large barrier islands that are backed by a gigantic, very vast salt marsh, okay? And then we have the mainland here. And some of these that you might be familiar with, Jekyll Island and St. Simon's Island because those are very close to us. But there are several of these that run up and down the coast. So barrier islands are very, very important to us here in Georgia. Here's an example of one of the barrier islands on Georgia's coast. This is St. Simon's, and of course here's our causeway. We have our big salt marsh back here, and we have our Atlantic Ocean over here. This is St. Simon's here, but you can actually see other islands here. This is Sea Island. We've talked about Sea Island before. And then this is Little St. Simon's right here. So this is pretty typical of what we see on the coast of Georgia. We see barrier islands that are separated by tidal inlets. We see salt marshes around them. And you can even see this guy, little guy here. Here's a tidal inlet here for Sea Island and a tidal inlet here that separates Sea Island and Little St. Simon's, right? And it's backed by a salt marsh back into another barrier island, actually. Now we have these running all up and down the coast of the United States. On the east coast only, though, from basically the coast of Long Island. We saw Fire Island in our previous lecture when we talked about beach profiles, and that's all the way up near New York City. And then these run all the way down the east coast to the tip of Florida, and actually around on the other side and in the Gulf of Mexico as well. However, we don't tend to see these on the west coast of the United States, and that's because barrier islands only occur in particular places. First of all, you have to have a lot of sand. Barrier islands are made out of sand, okay? So you have to have an abundant sand supply, and then you need to have gently sloping bottom topography, which is what we have here on the east coast. We can actually compare the east coast to the west coast, and really what we're thinking about here is the continental shelf. So the east coast tends to be gently sloping from mountains that are relatively far inland, okay? Gently sloping down to the beaches. And then the continental shelf gently slopes until we get to the continental slope. But on the west coast, we have mountains that come straight down to the coast, and then the continental shelf is very, very narrow, and then the slope is right there. So rather than collecting onto the shore in barrier islands, what we see instead is that sediments tend to slump down this continental shelf and down the slope on the west coast and don't collect into these barrier islands. Barrier islands have a pretty consistent anatomy that we see repeated around the world, any place that we have barrier islands. So let's look at this particular diagram and talk about different parts of barrier islands. So in this diagram, all the way to your right, this is where the ocean would be. And of course, we have the beach here. We've talked about the idea of having longshore bars and troughs, right? And then we have beaches here. We tend to have a berm here, right? And especially in summer, we have that berm that goes up onto the beach, and that transitions into dunes. Now, sometimes we get these overwash fans. When we have big storms, waves can push sand up and over the dunes and into something called an overwash fan that will push sand from the ocean side of the island into the middle of it. So these are pretty commonly found, okay? Behind the dunes, we tend to find things like grasslands or forest, and especially here in Georgia, we see maritime forests here, and these are characterized by beautiful big live oaks. So we have forests typically on our barrier islands, and then as we move further away from the beach, we get to sort of the far end of the barrier island, and this transitions into salt marsh. We have two different levels of salt marsh. We have high marsh here, which is the part of the marsh that is a little bit drier. It only is inundated at high marsh or even during spring tide. So this is not flooded as often. And then we have low marsh, and this is flooded more often by the tides. Quite often, these will be bordered by sand flats, and these go down into some sort of tidal creek back here, okay, or a lagoon back in here. Now, just as we have consistent anatomy on the top, on our topography of the barrier island, we also have consistent geological trends that occur in barrier islands that we see underneath the surface. Quite often we see down here underneath our soil, we see something called peat, all right? And this peat is actually salt marsh that has been covered over by things like sand and soil, all right? So you see peat here, okay? We also tend to see, we'll see different types of peat where we have low marsh peat and high marsh peat. Okay, we see soil, and as we are up into these sort of upland areas, we see more organic materials, and then we see sands here. Okay, so this, if we take if we were to take a core here, these cores can tell us a lot about what's below our barrier islands, and typically these are the things that we find below barrier islands. Okay. So these are composed of thick deposits of sand and peat. They run parallel to the coast. They tend to be relatively thin, maybe a mile or two across, but then also very, very long, and they are separated from the mainland by tidal creeks or salt marsh. So this is the general trend of what happens with barrier islands. So how do barrier islands form? One of the things I want you to remember is that our sea level has not been consistent over time on this planet. Our sea level rises and falls, and we see evidence of that here in Georgia. So let's just look at this diagram here, this map of the coast. So this is present day coast, okay? This is St. Mary's River. So this below this is Florida, above this is Georgia, okay? This is Jekyll Island, this is St. Simon's Island, so we're right about here, okay? And this is the ocean out here. This is the present day coastline, all right? And we can see changes in elevation as we move from the coastline inland, and we can see this is very low lying, so this is elevation here, right? So light blue is low elevation. So we have kind of a coastal plain here. And then as we move inland, we jump up in elevation, okay? And what we actually see when we map elevation is we see a series of ridges that occur as we move inland. And see this one right here, this is called the Trail Ridge. And this is an ancient coastline, basically. These are ancient dunes from long ago. And you can actually, as you're driving inland, it'll be flat, 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 and all of a sudden you'll start to go up this hill. You're driving up an ancient sand dune, basically, as you are moving inland, okay? So the coast of Georgia is a series of these ridges. So this is the Trail Ridge here that is right here, okay? And these are ancient sand dunes and also ancient barrier islands. So we see these series of barrier islands and sand dunes that are basically occurring in parallel to today's coast, all right? So we have today's coastline. And yellow here is modern deposits. And then this red, okay, this is from the Pleistocene area. The Pleistocene era. We're in the Holocene right now. That's our current era. The Pleistocene is the one just before this. And so parts of our current barrier islands were formed many thousands of years ago. And then parts of them were formed today. So we're going to look a little bit at how this occurs. All right, so this is Jekyll Island, and this dotted line is the current coastline of Jekyll Island, okay? But what we find when we dig down into Jekyll Island, we see evidence that this actually was formed, the middle of it was formed in the Pleistocene. So 50,000 years ago, there was an island here that looked like this, okay? And our sea level, it receded sometimes, it advanced sometimes, based on what's happening with the climate of our world. So this stayed around, right? Even when sea level changed, we had this the remnant of this barrier island. And when sea level started to come back, so a long time ago, 50,000 years ago, sea level was way, way, way out to the east because we were in the middle of an ice age and water was captured in the glaciers at the poles. So sea level was way, way far away, but as sea level started to come back, as the ocean started to come back, this barrier island reformed. So this is about 5,000 years ago where we had the remnant of the Pleistocene barrier island here. And then we had new island forming. The Holocene, again, is the era that we live in now. So this Pleistocene part sort of formed the beginning of modern Jekyll, and it grew out from there. And then eventually this got pushed back because this is a dynamic shoreline, remember, this got pushed back into what we see today. So now we have, this is all salt marsh back here. The middle of Jekyll is of Pleistocene origin. So this is all about 50,000 years ago. And then we see on the edges of this, we see new parts of the island that have been formed in our current era, okay? And actually, if you see this, this is called the Silver Bluff Shoreline. Well, there's a new microbrewery opening in downtown Brunswick, which is called Silver Bluff Brewing, and that's where they get that name from, because a lot of our islands are part of the Silver Bluff, which is the very old barrier islands. So what does this actually look like when we take a cross section? What we see is that we have this old Pleistocene island here that sort of forms the bottom of Jekyll and the very middle of it as well. And then we see this is the ocean out here. We see the ocean is very muddy inlet fill, so mud that washed out from the inlets. And then we have sands that are basically overcovering that into the ocean. And then we have dunes on top of that, okay? So the middle of it is Pleistocene. And then all of this sandy stuff is forming on top of mud that came from the inlets. Okay, so this is towards the ocean. If we look at away from the ocean, this is Jekyll Creek, and we see inlet fill. So basically, these are sediments that are coming, muddy sediments that are coming from inland, and then we have marsh forming on top of that. So this is sort of what a cross section of Jekyll Island looks like. And we can see when we look at the topography of Jekyll, this is where the campground is. So this is the north end. This is that road that goes all the way around. Okay, so this is the campground here. This is, up here is Driftwood Beach. Okay, and you can park here and you can walk out. Maybe many of you have done that. Okay, so all this middle part here, these upland parts, this is Pleistocene. This was formed 50,000 years ago at least. Okay, so this was that sort of previous set of barrier islands. And then all of this north of this has grown in our Holocene era. Okay, and you can actually see a series here of dunes that are parallel to the coast. All right. And then we have Driftwood Beach up here. Now, the interesting thing about Driftwood Beach is that all those trees that are dying, well, that's maritime forest. And basically, that maritime forest, this shore is eroding away slowly and eroding into the forest. And those trees that you see are from that forest, okay? So that's what you are seeing when you go up to Driftwood Beach. You're seeing a Holocene barrier island that has basically formed around a Pleistocene barrier island, and that is constantly changing and constantly eroding. So then how do barrier islands form? There are three different ways that they form, okay? So one way that they form is we have sand ridges that get isolated by rising sea level. We have sea spits breaching during storms, and we have the vertical growth and emergence of longshore sandbars. And here's an example of this middle, this second method, which is where sand spits get breached during a storm. So this is Blackbeard Island here. Okay, and this in here is Sapelo Island, and they're separated by, this is salt marsh, and then this is a tidal lagoon, basically a tidal creek, okay? And we have an inlet here, a tidal inlet here. And for many years, as this started to curve, so water travels faster around the outside of a curve than the inside of a curve. So this water here started to erode away this beach, and you can see it's very, very narrow. I went to this site about 3 years ago, and this I landed a kayak right here. We walked across, and it was maybe only, I don't know, 100 meters across here. So this was very, very thin. And then Hurricane Irma came along. And in Hurricane Irma, there was such strong wave action and so much tidal action because of the surge here in this creek that we had this breach occur. So this is that site where this right here is right here. So it breached through, it separated this part of Blackbeard Island from Little Blackbeard Island, this is called, okay? And so now we have a new barrier island that is here, and this may migrate south and join this island. This is called Cabretta Island, so it might migrate south, you never know, and that means that this inlet would close up and that this inlet would get larger. That's something that might happen to it. And so geologists are watching this and very interested in what's going to happen to our new barrier island here in Georgia. Another thing that can happen is you can have an offshore bar that that is exposed and grows. So if we have a beach here, and remember we talked about the idea that we have these longshore bars, these bars can grow, and sometimes they can grow large enough that that they're exposed long enough that you end up with some vegetation on them, and that vegetation captures sand, and then this can grow from a bar into an island. I couldn't find any good examples of that, but it does exist. Barrier islands are dynamic. They're part of this dynamic shoreline, and they're constantly moving. They migrate, and they tend to migrate from the ocean towards the shore. All right, so we have an example here of how barrier islands move. This is our ocean over here, and these are our tidal creeks over here. And remember, we have this peat here that is basically salt. Remember, there's a lot of salt marsh back in here, and that salt marsh, as it gets covered, it becomes peat. Okay, so this is the original profile here, and over time, this barrier island will be pushed away from the ocean because of wave action and wind action. Will be pushed from this side to the other, and it will actually cover over the salt marshes that are here. So this is the original island. Here it's moving further landward, and again further landward and further landward. So this is the original profile right here, all right? This little dotted line, and this island has moved from ocean side towards the mainland side. And quite often you see peat outcroppings then right along the beach here. When you see peat outcropping, what you're seeing is ancient salt marsh actually. So we have some pictures here of what happens when we have barrier islands that migrate. First of all, if you build a house and you build it like here, and that beach migrates away and it moves inland, then you may end up with a house that is in the water, and this happens all the time, all along our barrier islands. Unfortunately, you and I get to pay for the flood insurance for this house, and I don't know if that's particularly fair. That's my personal statement there. So this happens all up and down our barrier islands. But then also here is, remember we talked about this peat, this idea this peat is old salt marsh that's being exposed. Well, so this is a beach. This is actually Sapelo Island here, and this over here is Cabretta Island, and there's a tidal creek between them. And what we're seeing, this dark stuff right here, this is the peat. So this is ancient salt marsh that was covered over by sand for thousands upon thousands of years and is being exposed as the beach is washing into this direction. It's washing from east to west. Because barrier islands can migrate, they can actually keep up with sea level rise. So remember we talked about the fact that sea level is not constant. It changes over time depending on what our climate is. And so let's look at this graph here. So this is time on the x-axis. This is today, and this is thousands of years ago, okay? And then sea level is here on our y-axis, and this is modern sea level is right here. So if we go back 20,000 years ago, sea level was, 130 meters below where it is today. That means that our shoreline was miles and miles to our east, okay? Now, as our climate warmed and the glaciers melted, that water was liberated, and our sea level rose to where it is today. And of course, sea level is rising very, very quickly now because of climate change. And that means that we expect that many of our coastal environments are going to be inundated. And it's a big challenge for us here, and will be a challenge for you in your lifetime. All right. So what happens to barrier islands as sea level rises? So let's just take a look at this. Let's take a look at this diagram here. So this shows us 15,000 years ago. Okay, there was a beach ridge here. All right, and that would have been something like a dune. All right, and this sea level would be rising. As it rose, this beach ridge became a barrier island with a lagoon behind it. And you can see that the trees that were here died, and we have salt marsh that's growing here. All right, so we have, this was the first sea level, this is the second sea level. Now, as sea level rises, wind continues to push sand from one side of the island to the other, and waves also continue to push sand from one side of the island to the other. And so this barrier island actually will move along with sea level. All right, so this means that this barrier island can actually walk along the coast as sea level is rising, and this typically happens. We see examples of it because we have so much fluctuation in sea level with the climate. We see the series of ridges that I showed you earlier in the lecture. Well, folks, we're going to go ahead and stop this lecture here. It's a good sort of stopping point between topics, and I hope you're all well. Let me know what's going on, and make sure you're answering the questions that are attached to these lectures in D2L. Everyone have a great day. Bye.